Hi, I'm Krishna Kumar. This is a short preview of the midterm assessment that we did on the red wine dataset. I'm going to do a very quick preview of um, how I approach this problem, and this is a short presentation on the results. So let me get started. First, I'll go with the data distribution. As you see, I've done the scatter plots for citric acid, chlorides, sulfur dioxide, pH against the quality. And from these scatter plots, it's not very evident if there's a linear relationship or a nonlinear relationship between the respective variables and the target variable quality. So you'll need to investigate other aspects before we can come to a conclusion if there is a linear relationship or not. Next, we will analyze some of the distributions. As we see for each of these, this is also called as univariate analysis. So as we see in citric acid, there are 5 variables in total. Citric acid has a positive skewness. Uh, pH is a normal distribution. In chlorides and sulfur dioxide have positively skewed. Uh, Only pH here has normal distribution. Similarly, alcohol is also exhibiting positive skew or right side skew. The quality here looks seems to be like a normal distribution. So now we will, wherever we are observing skews, we have to apply transformation and normalization so that we bring all variables on the same scale before applying the model. So, I explored some of the transformation for each of the variables, and we are going to see what are those. So in the first case for citric acid, the initial skewness was 0.46. After I applied log transformation, the skewness came down to 0.18. From the uh, distribution plot, it is not very evident that it is symmetrical, but the skewness has certainly reduced. Similarly, for chlorides, the skewness was very high, 6.51, positively skewed. After applying polynomial transformation, that is to the power of zero point 0.2, the skewness has reduced to 3.04. I would still say the skewness is high, but uh, we can go with this. For sulfur dioxide, the skewness has significantly reduced from being a highly positively skewed to normal distribution. It has come down from 1.88 to minus 0.06, and this is after the log transformation. For alcohol, it's highly positively skewed. It is positively skewed, not moderately positively skewed. After log transformation, this has come down to 0.68. Quality variable is already normally distributed, so I didn't apply any transformation on this, only applied normalization. So as we saw in all these cases, after applying transformation, we applied min-max um, normalization so that I bring all the variables in the range of 0 to 1. Then the models were applied, and these are some of the model results. So there were 4 algorithms in total which were applied on these 4 variables. Uh, pH, since it had a very uh, low correlation with the target variable, that was eliminated, and using those 4 variables, remaining 4 variables, citric acid, uh, chlorides, sulfur dioxide, and alcohol, this model was derived. And as you see in this table, the RMSE scores has been listed along with the average absolute error and Pearson and Spearman correlation. So we see that we applied 4 different algorithms. With these 4 algorithms, OWA, that is ordered weighted average, got me the least RMSE. Got the least RMSE. So hence I am using this algorithm going forward in my prediction. This table summarizes the weights. Since I'm selected OWA, which is having the least error, the weights for this is highlighted. and ordered weighted average gives more weights to the higher input variables uh, than the low inputs. That's one of the feature of OWA. So W3 and W4 um, have more weightage in the prediction of quality. That is the inference from this table. Coming to the correlation table, as we discussed earlier, so um, here I have listed both Pearson and Spearman correlation. So as you see, most of the variables are positively correlated or negatively correlated with quality, except pH. pH has correlation close to zero, which means it does not exhibit any sort of relationship with the quality. Hence, I excluded this variable during the modeling process. Also, another important observation is alcohol has the highest correlation, followed by citric acid. So it is quite possible that alcohol has a higher uh, impact in determining the quality of wine. So based on these results, the conclusion is that the most important variables uh, in this case, since we are using ordered weighted average, is uh, alcohol as the highest uh, impact, followed by sulfur dioxide, and followed by chlorides and citric acid, uh, which has a weight of 0. So alcohol and sulfur dioxide is going to play a very important role in determining the quality of wine. So based on my experiments, figured out that ordered weighted average is the best fitting model. And for the test data that was given, which I have listed in 5B, uh, I ignored pH because it has low correlation. Considering other four inputs, the quality I got was close to 3.13. After rounding it off, it is 3. So that was the answer I got, predicted output. Uh, I'm convinced with this prediction because if I looked at the scatter plots, the range of the scatter plots on the x-axis for alcohol is from 8.7 to 14. Uh, so if you looked at that graph, lower alcohol, uh, I can infer that lower alcohol percentage leads to lower quality, whereas higher uh, alcohol percentage will lead to higher quality. So in this case, I got answer as 3, and in this case, you also observe that the alcohol percentage is 8.3, which is pretty low on that scale of 8, 8.7 to 14. So it can be inferred that maybe the alcohol, since the alcohol percentage is low, the quality also should be low. So 3 actually is on a lower scale of quality. Um, when we observe, since the range of the quality is from 3 to 8. Also, we observe that the RNS value is 0.87, which states that higher input values um, will play a bigger role in the determining the quality of wine. So in this case, the bigger values are alcohol and sulfur dioxide. So these two variables play a higher role compared to, let's say, citric acid or chlorides. Hence, I'm convinced with this result. So, in case if I have to, suggest somebody, what are the best conditions which a higher quality of wine will occur based on the experience of looking at this data and the models, I would say that alcohol, higher alcohol percentage will produce better wines. Higher sulfur dioxide content also will play important role in uh, preparation of wines. The minor contributors being citric acid and chloride. So citric acid, uh, in this case, has the least weight, but uh, cit- you know, my domain perspective, citric acid and chlorides provide the taste, so that will also play a very minor role, but in determining the quality, but they are minor contributors. Finally, I've chosen, comment the implication and limitations of the fitting model. So I've chosen OWA model for prediction. OWA is very ideal when rank-based emphasis is critical, such as focusing on best or worst input values. So in this case, I'm looking at the best values of wine. So I should rank whichever inputs have higher values that will play a major role in getting me the best quality of wine. That is one way of looking at it. Also, OWA is ideal when when I have to explain the models to the stakeholders. So this is more of a white box approach rather than black box approach. In other algorithms, it is like deep learning models. It is very difficult to explain this weightage or coefficient because it's very complex. Um, so this is a case of optimistic aggregation. Um, this is a case of optimistic aggregation where I would prioritize the highest uh, value. Uh, so I would conclude that um, OWA is ideal, and rank-based emphasis is critical. Finally, on the limitation side, OWA has uh, serious limitations in learning complex and non-linear relationships between inputs and outputs. Also, OWA cannot handle large feature spaces effectively with feature importance rankings. So for tasks requiring complex interactions and high dimensional data sets, um, where I don't need, let's say, explainability, I just am bothered about accuracy, I will go with other machine learning models other than um, linear models, like random forest or tree-based or deep learning algorithms. Um, so that is a limitation of OWA. However, it is very useful when you're dealing with uh, rank-based emphasis is required. That's my overall summary. Um, so this is the conclusion I would like to give. Um, I've also summarized some of these points in the notebook. Um, thank you.